Good evening, everybody. Trust you guys are doing well this evening. Let's make sure this audio is working. It looks like we're up and running here. You guys have any family lives down in the Gulf? Looks like they're getting hit pretty badly with that hurricane. All right, I'm gonna run grab me a cup of coffee. I'll be right back. Oh yeah. Are they near where they're the hurricane's hitting on the west side of the Gulf there? West side of Florida? Not west side of the Gulf, but Tampa and up through there? Do you guys have any questions this evening about rational functions, graphing, asymptotes, vertical, horizontal? Oh, it's not going well at all. And not well if they're down there. Right now, it's a mandatory evacuation for anybody on that west side of Florida. It's mandatory evacuation. Hurricane Helene is about level 4, supposed to be hitting in the next hour or so this evening. Everybody feeling good about rational functions? Everything going okay? Yeah, you will have to. Yes, Haley. There's at least one in the homework where you find the curved asymptote. Let's just go back through our notes again. Let's review a little bit about asymptote, shall we? How do I find vertical asymptotes, everybody? Remember, we looked at the function R of X is equal to P of X, P of X divided by Q of X. Right, exactly. You guys are both correct. We take a look at this denominator, Q of X. So for the vertical asymptotes, we let Q of X not equal to 0, and we solve for X. All right? We set the denominator equal, not equal to 0, and solve for X. That tells you that X, the vertical, well, that's the domain, actually. That's the domain. It's equal to 0. That is the vertical asymptote. So I should say equal to 0 here. All right, and solve for X. All right, how do I find the I'll call them non-vertical, non-vertical asymptotes? How do I find those guys? What is it I'm doing? Google. There you go. Ask my friend, right? Ask my friend. Hey, Google, what's up? Help me out here. I'm just saying. Yeah, you look at the degree, right? Exactly. You look at the degree. You compare the degree of P of X and Q of X, and you have a ratio, exactly the ratio of the leading coefficients, right? And then you look at the exponents. So
Oh, I can't do it from my phone. I need to scan it. I usually do it like on the computer and I scan it.
are you realizing that you're talking to the class?
Hold on, wait, scan it on my log in there. I literally just have to put my name.
We're going to mute you. Thank you. All right. So we are looking at the degree of the leading terms of P of X and Q of X. If the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote of y equals 0. If the degree of the numerator equals the degree of the denominator, we have a vertical asymptote that consists of a ratio, like Justin said, the ratio of the leading coefficients. If the degree of the numerator is 1 greater than the degree of the denominator, we have a linear equation, that's the asymptote. If the degree is 2 greater, you have a parabola. That's how you guys know, right? If the numerator is heavier by a degree of 2, you're going to have a parabolic asymptote. Okay, that's how you know. So those are the 4 types of non-vertical asymptotes that you'll be looking at. Horizontal, where the degree of P of X is less than the degree of Q of X. Horizontal, where the degree of P of X equals a degree. And non-horizontal, where the degree of the numerator is greater than the degree of the denominator. All right, let's just give ourselves a 4 example. Okay, let's just to make sure we're all on track here. Suppose I give you this function. I tell you that I have a function f of x that is equal to negative 3x squared minus 4x plus 5 divided by negative 3x minus 1. Determine everything you guys can about this function, okay? Everything you can about that function. What's the domain? What's the vertical asymptote? Does it have a horizontal asymptote? Does it have a slant asymptote? Does it have a parabolic asymptote? Does it have intercepts? Does it have a y-intercept? Does it have an x-intercept? What can we tell ourselves about this function? Just like we did last Tuesday night together, 2 or 3 times. Yep. Vertical asymptote. Yeah, we can talk about that, Kelsey. It's there. There's one in the homework. All right. So the vertical asymptote. If we want to start here, the vertical asymptote, we set negative 3x minus 1 equals 0. Negative 3x equals positive 1. X equals negative 1/3. That's our vertical asymptote. That tells me the domain. The domain is x cannot equal negative 1/3. All right. So those are the easiest two, everybody. Well, there's one more that's really super easy, and that is the y-intercept is super easy. All right. The y-intercept is when x equals 0. So what is f of 0? That's my y-intercept. It looks like it is 5 over negative 1, which equals negative 5. Yep. Perfect. So we've done all the easy ones. We know the vertical asymptote, we know the domain, and we know the y-intercept. Those are easy. And Justin says we're going to have a slant asymptote. Okay, we're going to do synthetic division, everybody. So you can do long division, synthetic division. I don't care which one it is, but you have to divide the numerator by the denominator. Divide by whatever you want to divide by. What I'm saying is synthetic division or long division. I don't care. If you did synthetic division, right? You look for the value right here in this box, the value that makes this 0. What makes this 0, everybody? We just did it down here. Negative 1/3, right? So you put negative 1/3 here. I know that's not easy to see. Let me back that out of there. You put negative 1/3 right there. Then here you'd put negative 3, negative 4, and 5. Now you do your synthetic division. What's step 1 for synthetic division, everybody? What's step 1?
Bring the 3 down, negative 3 down.
Right, just bring the negative 3 down. All right. Now I multiply. Negative 1/3 times negative 3 is 1. Negative 4 plus 1 is negative 3. Negative 1/3 times negative 3 is 1. That's 6. There's my slant asymptote right there. Y equals negative 3x minus 3. Now let's see if we did that right. Let's check our long division and see if we did this correct. negative 3x minus 1 divided into negative 3x squared minus 4x plus 5. All right, negative 3x goes into negative 3x squared. That would be x right there, right? That would be x. X times negative 3x is negative 3x squared. X times negative 1 is negative x. Add and I get negative 3x. Negative 3x goes to negative 3x plus 1. So that would be x plus 1. So something's different there. That's kind of weird. It's kind of weird. It may be better for us to do long division if that coefficient of x isn't a positive 1. It may be easier to use long division. It may be more straightforward for us. All right, so we have a slant asymptote. We have a vertical asymptote. Remember, this is the line y equals x plus 1. That's our slant. We know our vertical, we know our domain, we know our y-intercept, we know a bunch of things. We could go ahead and graph this thing without too much trouble at this time. All right, now the question was, Kelsey asked, what if it is a curved asymptote? Let's look at one of those. All right, if it's a curved asymptote, the degree of the numerator has to be greater by 2, right? So it could be something like, suppose I had 2x cubed minus 4x squared plus 6x plus 1 divided by x plus 2. All right, something like that. That is going to be a parabolic asymptote. It's going to be a parabola because the degree of the numerator is greater than the degree of the denominator by 2. And this one you could easily do with synthetic division because this is not going to leave you with any fractions to cause you any problems. All right, so you could just go up here. You could say, what makes this 0? It's negative 2. All right, you could put in here 2, negative 4, 6, 1, bring the 2 down. That's negative 4. Add, you get negative 8. Negative 2 times negative 8 is positive 16. That is positive 22. And you don't have to worry about the rest of it. This is my parabola right here. That is the graph y equals 2x squared minus 8x plus 22. That is your asymptote right there. The vertical asymptote is at x equals negative 2. It doesn't have a horizontal asymptote. It has a parabolic asymptote. Let's take a look at it just for fun, shall we? Let's go to Desmos. And let's put our function in here. F of x equals, I'm going to use a parabola, I'm in parentheses to get it started, 2x cubed 2x cubed minus 4x squared plus 6x. Whoops, wrong place. Here we go. Plus 6x plus 1 divided by x plus 2. All right. You can see some funky stuff going on there, right, everybody? That's pretty interesting. Then here is your parabola right there. That's going to be your parabola. Remember our vertical asymptote was x equals -2. So we'll put in here x equals -2. Whoops. And there you have it. You can make that a vertical dash line by just going to Desmos. All right, let's make this a little bit easier to see for ourselves. All right, let's let the y-axis go from -10 to 100 by 20. All right, there you can kind of see what's going on. And we can put our asymptote in. It'll be y equals 2x squared minus 8x plus 22. And there you can see it. See how our graph goes on the outside of that parabola there, and this other part of our graph is inside the parabola there. So we can see exactly how all of that fits in together. Scott, you said, can you plug that in for the parabola? Do you mean what I just did, graphing the parabola?
Yep, that's what I meant.
Okay, perfect. All right, everybody, what do you think? Any questions? Kelsey, does that help? All right. All right, we'll go ahead and save this. I'll drop that in here for you guys if you want to take a look at it sometime later, if you want to use it for anything. All right, let's go take a look back here, see what's next. All right, so we did graphing rational functions. Let's just dip in here for a second. Then we're going to go take a look at some composite functions. So let's go right here for a moment tonight. Oops, not the homework. I mean, not the video. We don't want to see that. Let's go right here. You guys may want to do some work here. Only 46% of us have started it. So let's start right here. Oh, before I go there, I'm going to go here. I think there was one here that I was working on today that was parabolic. Yeah, here it is, Kelsey, right there. Question number 11. That has a parabola asymptote right there because that's 2x cubed and that's x plus 1. Therefore, that's going to be a parabolic asymptote like we just did. %92 of you guys have started this. Does anybody have any questions right here you'd like me to discuss before we take a look at the graphing ones? Anybody have any questions here? Looks like a lot of you are done here. Which question do you guys think is the most difficult? Questions 1 through 13 here. Which one do you think is the most difficult? It looks to me like, let's see. Looks like question number 5 is the most difficult. That's the one that most people are taking a longer time and they're getting it right on the third try. All right, what's question 5? Use the graph to find the asymptotes. Okay. Remember the asymptotes would be vertical asymptotes here, right? Horizontal asymptotes here. So you can zoom in and out on that one. But it looks like most of you have gotten that right. 14 of you have. Number 7 says below is the graph of a rational function. Find the asymptotes. That's a slant asymptote, right, guys? So you're gonna have to use the equation of a line, right, to figure that out. Does it look to you guys like there are vertical asymptotes? It looks like it to me, right? It looks like right up through here, there's vertical asymptotes. There's a slant asymptote, therefore there cannot be a horizontal asymptote, right? All right, good. Again, anybody have any questions here you're working on you'd like me to take a look at with you? All right. Let's go take a look at some graphing questions. These questions are due tomorrow evening. All right. So if you guys haven't started this yet, go ahead and jump in here with me right now. Okay. You only got 8 questions. So we could get a lot of this done tonight, everybody. Just jump in and let's do it. It says graph or consider the rational function, give the domain by listing all the values. Okay. List the x coordinates of the x-intercepts. List the location of the vertical asymptotes. Okay. List the x values for which f has a missing point, removable discontinuity. All right, guys. So talk to me about a removable discontinuity. What does that mean, and how do I notice it? We did this last time together, but it was not a main topic, so it may have been forgotten. Yeah, it's an undefined point, right? And how do I come across an undefined point, Kelsey? When would that arise? Or anybody? When would that arise? How will I have an undefined point? Well, in this case, Matt, that's a good suggestion. If they have a shared factor, right here, everybody look, right here. When I factor these, I can cancel this out, and we say to ourselves, we know that x plus 5 divided by x plus 5 is 1. So I can factor that out and cancel it out. But when I come down here, it's going to have to be noted right here that I have a removable discontinuity, right? Because x cannot be -5 according to that factor right there. So in my domain, I have x cannot equal -4, x cannot equal +3, and x cannot equal -5, right? That's in my domain. But then I cancel it out. When I go to graph it, it's going to look like it's continuous through there, but it's not going to be continuous because it's going to have a hole in my graph, right? It's going to have a hole. So when you're looking at these questions, that's what you're asking yourself. Is there a factor that I can cancel out? That's a removable discontinuity. Okay. It's going to leave a hole though in my graph. All right. The next question says, list the x coordinates of the x-intercepts. Everybody, how do I find x-intercepts? What has to happen? In order for my x-intercept, let's just look at a picture for just a second. We're just making a little small picture here. Here's my x-axis, here's my y. In order to have an x-intercept, what has to be the case? That implies, right, that y equals 0. All right, that's what it implies. What's the only way for this function to be 0? The only way for it to be 0 is for the numerator to be 0, right? That's the only way. It's a fraction. The only way a fraction can be 0 is if the numerator is 0. If the denominator is 0, it's undefined. If the numerator is 0, the function is 0. So these are all my possible intercepts right there, right? X is -6, X is 2, X is -5. But once again, that's removable. All right. So in order to find the intercepts, I'm going to set this equal to 0 right here. That's what I'm going to do. All right. Next it says, list the location of the vertical asymptotes. Well, that's just my domain, right? It's just this right here. It's exactly that. X equals -4, X equals +3, X equals -5. All right. And then like I said before, the removable discontinuity is when my factors divide out. But last time we looked at a graph, we noticed that we have a hole there. Even though we divided the factors out, we're still left with a hole. All right, so if you haven't tried this question yet, it looks like we've had 17 attempts. We've had 3 people get it correct. So if you haven't tried this one yet, give it a try. If you haven't gotten it correct, give it a try. Jump in and see what you can do. If in doubt, ask your friend Desmos. If in doubt, graph this function, right? If in doubt, graph the function. See what it looks like when you graph it. Then down here it says, at the smaller x-intercept, describe the behavior of the function. Is it crossing the x-axis? It crosses but does not touch it. What's the smaller x-intercept? Well, the smallest one is x equals -5. Right here at x equals -4, it touches it but doesn't cross it. How do I know that? Because it's squared, right? Remember, when my function is squared, that's where my graph touches the axis but doesn't cross it. All right, at the larger x-intercept, describe what happens. Where's my larger x-intercept? At x equals 3. That's where my graph crosses that x-axis. All right, then it talks about what happens at the vertical asymptotes. Once again, everybody, in case of doubt, graph the function. Notice that the degree of the denominator is greater than the degree of the numerator. Everybody notice that? The degree of the numerator is x cubed. The degree of the denominator is x to the 4th. Therefore, we know that it has a horizontal asymptote at y equals 0. Okay, we know that. Okay, so let's try it. We're going to call it g of x. All right, we have x plus 6 times x minus 2. Well, this is mine, it's probably not yours, times x plus 5. All right, divided by x plus 4 squared. That gets kind of weird on us right there. Times x minus 3 times x plus 5. Let's shut this one down so we can't see it. We're looking for the green graph. Blue graph, rather. There, you see it. You can see there's our vertical asymptote right there. There's our other vertical asymptote right there, x equals 3, x equals -4. At x equals -5, if I put in f of -5 or g of -5, look, everybody, g of -5. That's undefined. That's where my removable factor was, right? All right, what else do we notice from here? Where are my x-intercepts? Notice right here, we said we had an x-intercept where this equals 0. It is -6. Let's change the color. -6, we have right there, right? At 2, right there. And at -5, it's gone, right? It's canceled out. It's gone. So there from the graph, you can see what happens with our x-intercepts. We can see our vertical asymptotes. We can see everything we want to about this graph. You can see we have a horizontal asymptote right there at y equals 0. All right, notice if we zoom out on this just a little bit, this graph crosses it, but it comes back up to it, right? It comes right back up to 0. This graph comes down to it, but never crosses it. This graph dips down through it and goes away very quickly towards negative infinity. So there you go. If you have any questions about your function, just take a second, graph it, and look what's happening. All right, the next one's taking us even longer. So let's take a look at this one. It says graph the rational function below on paper by hand, then do the steps that follow to confirm your work. Well, everybody, we can take a look at this function and we can see that it has vertical asymptotes at plus or minus 2, right? How can I tell that? Because the denominator tells me my vertical asymptotes. You can tell me that it has an x-intercept at x equals -1, because that's where my function is 0. All right. So I know I have vertical asymptotes at x equals plus or minus 2. All right. That's not proper here. There's x equals 2 right there, but I need one at x equals -2. Okay, right there. All right. Does this graph have a horizontal asymptote? It does. What do you guys tell me about the horizontal asymptote? Look at the function and tell me in the chat box what the horizontal asymptote is just by looking at it. Zero it is, right? It is 0. It's 0 because why? Somebody other than Scott. Why is it 0? Because Scott said so. What do you guys say? Why is it 0? Because the degree in the numerator is smaller degree in the denominator. Perfect, Kelsey. That's exactly it. So therefore, everybody, when I'm going to graph this function, I can scroll right down here. I can grab this orange line, right? Just grab this guy and drag it right up there. Now I know that. I know that much is true. Okay. Notice there it says it has an x-intercept at 0, a y-intercept at 0. Does it? Look up there. Is my x-intercept at 0? Once again, how do I find the x-intercept? That's where my function equals 0, right? Where does that function equal 0? Wherever the numerator equals 0. So f of x equals 0, where x equals what, everybody? f of x, f of x equals 0, where x equals what? You say, I don't know. I don't have a clue. Okay, that's okay. Take the numerator, x plus 1, set it equal to 0. What do you get? Well, if x plus 1 is set equal to 0, you get x equals -1, which tells me that the y-intercept, the x-intercept rather, has to be right there. All right. So now what do we have set? We have the vertical asymptote set. We have the x-intercept set. We have the horizontal asymptote set. The only thing we don't know is that point correct? Is that point correct? I don't know. How would I check to see if that point was correct? You tell me, well, I would find what? Caden, Shelby, Matt, what would you do? There you go. Plug 6 in. Exactly. Lauren and Justin, exactly. Plug it in and find out what is f of 6. Right? So all I got to do is plug it in and see if that point is correct. So I go right up here and I find out f of 6 equals 6 plus 1 divided by 6 squared minus 4, which is equal to 7 over -6. Yes, it is. Thank you. Which is 5. -6 squared is 36 minus 2, which is minus 4 rather. -32, right. 32, which is 5 over 32. So I have the point. This is -6. Yes, -6. I have the point -6, 5, 30 seconds. That's not going to work. Okay, so that point is not on my graph. So I need to move it so that it is. Means it has to be down here closer, right? Maybe I can't even find what point that is. What's 5 30 seconds if I divide that out to the decimal? I may need to look for another point. It's really close to 0. All right. Let's try another point instead of that one, right? I need to try a point that actually gives me a value I can plot easily. I can choose anything I want to over here, right? It just has to be something over here. Something that I could plot along the x-axis that gives me a point that's actually easy to work with. Something that is smaller than, all it has to be, right, is smaller than or more negative than -2. I could try f of -3 if I wanted to, which is -3 plus 1, which is -2, divided by -3 squared minus 4, which is 9 minus 4. Oh, it actually comes out negative, which is 5, which is -0.4. If I did the math correct. All right. So that's all I need to do. Find a point that works. If I'm in doubt, I can go right over here and I can type this guy out. I can go graph it in Desmos. Let's shut this down. All right, I'm going to make for myself a function x plus 1 divided by x squared minus 4. Yep, you can see that our function was upside down, right, everybody? Our function was upside down. When we're back here graphing it, we said it had to be negative something, right? This number has to be negative, like we said, it has to be down here. So that's about where we said it was supposed to be when we did the numbers ourselves. So we found out that our graph was actually on the wrong side of the function. And we can see it easily when we come back over here and check our work. So that's it. Step 1 here, everybody, I would find the vertical asymptotes. Step 2, find the horizontal asymptotes. Step 3, find the 1 point and just move that blue point to wherever it needs to go. All right, I can see lots of you guys have been working on it. So if you want to take a few minutes, let's just take a few minutes to work on some of these, okay? It is almost 8 o'clock, so let's take a few minutes and work on some of these questions. You guys have questions, just let me know. Some of you guys are already done. You can just keep on working ahead as you've been doing already. That's fine. Somebody asked me the other day, is it okay if I work ahead? Yeah, if you want to, it's okay. You never know when things may come up. You never know if you may need some time at another time. So yes, if you want to work ahead, feel free to do so if you get the opportunity. We have 8 questions. Let's see how many of these we can knock out here. Question number 3 is the same thing. They want you to pull the points to the right place. The green are the x-intercepts, the red are the vertical asymptotes, the orange is the horizontal asymptote. Then you got to choose a point.
Okay, now to guess now. Like this. So you guys think
Sounds like Megan has some good help there.
they should buy a vampire. A vampire.
Remember, you find the x-intercepts by letting your function equal 0. Your function equals 0 where the numerator equals 0. Once again, if you guys have any questions, let me know. I'm happy to work through a question with you. You're going to separate these answers by commas, right? Because you're making a list. If you guys haven't finished the previous lesson, I suggest you try a couple here to get yourself started. There's only 8 of them, so if you could get a couple of them done, you'd be well on your way. Looks like question number 7 has a slant asymptote, so be aware of that when you get there. Number 7 is a slant asymptote. That's why it gives you the two orange points determine your slant asymptote. So that's why you have that. So you can drag it correctly and put the points where it goes. So only one question with a slant asymptote according to my questions that I have. Probably the first question is the most complicated one of all. All right, we're going to work till about 8:20. That's about 12 more minutes. So work till about 8:20. And then I'm going to look at the lesson, which is composite functions, which is our last lesson to look at this week. So we have 3 things to look at this week. Analyzing rational functions, graphing rational functions, and looking at composite functions. Those are the 3 lessons for this week. And so at 8:20, about another 12 minutes, I'll take up that 3rd topic for the week. So I'll have you guys ready to complete the assignments by Sunday night. In the meantime, if you guys have any questions, I'm happy to answer them for you. You guys who haven't completed this homework lesson here from last night, you guys need to go ahead and do that. Really, you should knock this out tonight. This lesson is what gets you ready for the graphing. This lesson is way more simple than the graphing. So if you haven't completed this lesson, now would be the time to focus on it. If I were you guys, one thing I would do for myself, okay? I would make myself a sheet of paper, a sheet. On that, I would have all the rules for asymptotes so I could just go right down through them, right? I shouldn't be wondering to myself anymore at this point, how do I determine whether it has a slant asymptote or a horizontal asymptote? I shouldn't question that anymore. I should know. All right, how do I know if the horizontal asymptote is zero or if it's another constant? I shouldn't have to ask myself. I should know. So if you guys don't have that down pat, make yourself some notes. Go back to the guided notes if you have to. And where it talks about it on there, write it down plainly, step by step. That way, when you come down through here, you can look at these questions. You see a graph, you know exactly what the asymptotes are going to be. You can tell right away just by looking at it. If they ask you to find the graph given a function, the asymptotes given a function, you can look right away. So the most important thing here is you have that rule. That's what you need for this homework right here. This homework number 14, you need to have the rules for what defines the asymptotes. All right. Looks like you guys are getting some more questions done. That's awesome. We'll take just a couple more minutes and we'll jump into the next lesson so you guys can be ready for that one too. Okay, we got some more people started here. That's good. Alrighty, so let's spend the next hour together. Let's spend the next hour looking at this worksheet and working on homework questions together, shall we? So, in this guided notes, we're looking at composite functions. Composite functions, everybody, as you can see in the middle of the page here. Given two functions, f and g, their composition or composite functions is defined as follows. All right, so when you see this f composite g, that's how you say it, f composite g of x, I would write it with parentheses myself. All right, I would write it like this. I would say f of g of x is equal to f of g of x. That's the way I would say it, putting that in parentheses, okay? I think those were forgotten here. All right, so what does that mean, everybody? That simply means this much. If I write f of x, right, and I then write f of g of x, what does that mean? That means I'm replacing x with a function. X is a function by itself, right? X is a linear function, but I'm going to replace that function of x with a completely new function, g of x, whatever it might be. It doesn't matter, okay? That's what a composite function. Composite mean, remember everybody, means made up of more than one thing. That's what the word composite means. So if it's made up of more than one thing, it's made up of more than one function. So I take a function and put it within a function, and that's then called a composite function. All right. They want us to first of all start by evaluating the function h of t. All right, what is h of negative 2? H of negative 2 simply tells me to put negative 2 in place of h, right? So 3 times negative 2 squared plus negative 2. Negative 2 squared is 4. 3 times 4 is 12. Minus 2, which is 10. That's obviously not a composite function, right? That says h is a function of t. We want to find h of negative 2, meaning t is negative 2. All right. What about the next two? Well, the next one says I don't want to replace it with a constant. I want to replace it with a variable. So I look for h of 3a, which is equal to 3 times negative, not negative, sorry, positive, 3 times 3a squared plus 3a, which is equal to 3 times 9a squared plus 3a, which is equal to 27a squared plus 3a, right? That could be considered a composite function because I'm replacing the t with another function, 3a. So it's simply taking whatever that function was, multiplying that variable times 3. You guys can see right here I have 3t squared. Right here I have 27a squared. Why is it 27? Not just a factor of 3, because the 3 was squared as well. Therefore, it's multiplied by a factor of a square or 3 squared. Right here you can see I have 3a where before I just had t, because I've taken that factor of t, multiplied it by 3. All right, the next one is also considered a composite function because now I'm replacing it with more than just x, it's x minus 4. So this is equal to 3 times x minus 4 squared plus x minus 4. Now I have to square this binomial, right? When I square the binomial, you guys remember how we did that before? X squared, in other words, square the first term. Then for my middle term, I multiply 2, this exponent right here, 2 times x times negative 4, which is negative 8x. Then I square the negative 4, which is plus 16. And then I add x minus 4. Distribute the 3, and I get 3x squared minus 24x plus 18 plus x minus 4. This is a plus here, not multiplied by. Add my like terms, and I get 3x squared. I have negative 24x plus x, which is negative 23x. I have plus 18 minus 4, which is plus 14. And I'm done. Okay, so when I have a composite function, what does that mean again? It means to take that function, whatever it is, and replace every instance of my given variable. In this case, I was replacing t with x minus 4. I could replace it with any variable. It doesn't matter. Whatever I'm trying to replace it with, I have to be sure and to replace every single instance of that variable. Anybody have any questions here? All right, well, let's try some examples then. Let's go down here. Let's clear this out. And let's try some examples. All right, first of all, I would put a parenthesis around here. I would play f composite g of x, g composite f of t, f composite f of t. Okay. Now I would give it a try. F, remember f composite g of x is f of g of x. What does that mean? That means in place of x, in this function right here, right? In place of that, I'm going to put g of x. So if I have f of x equals x squared minus 4, that means this is equal to g of x squared minus 2 times g of x, right? In place of the x right here, right there. In place of x, I put g of x. So I have g of x squared. minus 2 times x, I put minus 2 times g of x. Right? Now, in place of g of x, I put what g of x is equal to. G of x is equal to 3x. So this is equal to 3x squared minus 2 times 3x, which is equal to 9x squared minus 6x. And I'm done. What did I do? I replaced x with 3x. All right, so I've completed the first question. All right, next. The next question is, what would be right here? What would be g of f of t? All right, so let's make ourselves a note of what that even means, okay? G composite f of t is equal to g of f of t. What does that mean? That means for every x right here, every x in g of x, I'm going to put f of t. So if I know that g of x is equal to 3x, then I know that g of f of t is equal to 3 times f of t, right? In place of x, I put f of t, which is equal to 3 times what was f of t? T squared minus 2t, which is equal to 3t squared minus 6t. All right, and I'm done. So it doesn't matter, everybody. It doesn't matter which way I go. Am I doing G composite F of T? Am I doing F composite G of X? The order doesn't matter at all. All that matters is that I take that function that has the variable, whether it's X or T, it doesn't matter what it is, and replace it with the function, okay? You guys try the last one. Try F of A. F composite F of A. Give it a shot and see what you get. So we're now on the third one. We want to find F of A. What is this going to be equal to? All right, I'll give you guys a couple minutes. When you feel confident with your answer and you're ready to take a look at it, just drop me a 1 in the chat box, okay? All right, so the first thing you guys are going to want to find, looks like we have one so far that's done. Good job. The first thing you want to find is what is f of a, right? What is f of a? Because I want to find the function right here in the middle. I want to find f of a right here. What is f of a? So if I go back and look over here, I know that f of x is x squared minus 2x. That tells me that f of a is equal to a squared minus 2a. Right? So now I want to take f of a and I want to put it back inside itself. F of a. Right? So in place of a, what am I going to put? In place of x back here, whatever you want to say, I'm going to put f of a. What is f of a? It's a squared minus 2. So f of a equals, what is f of a? It is a squared minus 2a. Well, let's make that more legible for us. That's hard to read. F of a is equal to a squared minus 2a squared minus 2 times a squared minus 2a. All right, that's what I'm doing. Everybody notice this was where x was, right? Going back here. Here's x squared. In place of x, what did I put? A squared minus 2a. That's f of a. Right here, this was minus 2x. In place of x, what did I put? A squared minus 2a. I simply made that substitution, right? I made the substitution and then I could simplify it from there. All right, if I simplify this, I'm going to have to square this binomial. So f of a. If I square this, I get a to the fourth minus 2 times a squared times negative 2a, which is negative 4a cubed, plus negative 2a squared, which is 4a squared, minus 2a squared plus 4a, which gives me a to the fourth minus 4a cubed plus 2a squared plus 4a. And I'm done. You say, well, that can be quite a bit of algebra. Well, it can be depending upon what the functions are, but just remember the basic rule we're following. The basic rule is take whatever that function is and replace the variable in the function with it. I had a function f of x. I want to replace the x with f of a, whatever f of a is. All righty, we got those taken care of, guys. Let's see what we have next on our agenda. All right, it says find two functions f and g such that m is equal to f composite g. There are several possible answers, or it says give several possible answers. All right, let's take a look. Here we have our function m of x, and we want to show that m of x is equal to f of g of x. All right, that's what we want to show. So what are some possible answers that we could use, everybody? What's a possible answer that we could use? We could say, well, I have a function f of x. I could say over here that f of x is equal to the square root of x plus 4, right? I could say that. Or I could put a 2 out front here. I could say this. Let's make this more legible. F of x equals 2 times the square root of x plus 4. All right, then everybody, what would g of x have to be equal to? In order to make this statement right here true, this one, in order to make this true, what would g of x have to be equal to? Right, 3x minus 1. Perfect. I need to have 2 of the square root of g of x is 4. G of x, looking back here, g of x must equal, like Scott said, 3x minus 1. So therefore, g of x equals 3x minus 1. All right? Can you guys think of any other possible answers we could use here? Anything else? Any other possible answers we could use that would set this up nicely for f of x and g of x? All right, no ideas? Here's another idea for you. What if I went over here and what if I said, all right, what about if f of x equals 2x plus 4? Okay, suppose I said that. Suppose I said f of x equals 2x plus 4. Then what would g of x have to be equal to? Exactly. G of x would have to equal this function right here, the square root of 3x minus 1. Exactly, right? So that when I put that into my function, f of g of x equals 2 times g of x plus 4, which is equal to 2 times the square root of 3x minus 1 plus 4, and I'm done. Okay, we've done 2 examples together. But that shows you exactly how you're going to be working on the questions in your homework, okay? You're going to take a function and say, well, how could I put 2 different functions together to make these to be the same? Yeah, you could do that as well. Perfect. Justin just gave you guys another one. There's one more in the chat box, okay? Write that one down. And you can see there's a factor of 2, right? 2 times the square root of 3x minus 1 plus 4. You could also factor a 2 out all the way out to the outside, right? You could have 2x as one function, and the other function on the inside would be the square root of 3x minus 1 plus 1 on the outside. And that'd be another option. So there's 4 of them right there, right? So just think of all the different ways you could combine these 2 functions to give you the composite function m of x. All right. It says the evaluation of a composite function can be thought of as a two-step process. Given the functions below, complete the table. All right, let's see if we can complete the table. Let's start out. All right, first of all, it says find v of x. And this right here is u of v, whoops, not f. Right? This is u of v of x. So what am I going to do? I'm going to find the value for v of x. Then I'm going to take that value and put it into u of x, right? It's a two-step process. Find the value of v, put that value into u. Okay, that's where I'm headed with this. So v of 9. V of 9 equals the square root of 9, which is 3. So the 3 right here. Now I want to find u of 3. Why? Because I'm putting v of x into u. So I want to find u of 3, which is equal to 1 over 3 squared minus 4, which is 1/5. All right, so 1/5. All right, you try a couple. All right, so step 1, find v of 4. What is v of 4? Whatever that answer is, plug it into u. All right, so what did you guys get for v of 4? What should go in my first column there? What's v of 4? 2, right? Exactly. V of 4 is 2. I'm taking the square root of 4, which is 2. So v of 4 equals the square root of 4, which is 2. Now, next, what is u of 2? That's the next step. What is u of 2? 1 over 2 squared minus 4, which is undefined. All right, very good. All right, next, what is v of 1? 1, perfect. What is u of 1? Negative 1/3, perfect. All right, what is v of 0? V of 0 is 0, right, everybody? The square root of 0 is 0. All right. What's u of 0? V of 0 equals the square root of 0 equals 0. U of 0 equals 1 over 0 minus 4, which is negative 1/4. So it is negative 1/4. All right. What is V of negative 4? Has to be real numbers, everybody. Stick with real numbers with me. You guys are correct. You got it. Okay. You guys are, it's 2i. That's 100% correct. But if it had to be a real number, you would tell me what? Undefined. Okay. Perfect. And since that's undefined, this over here is also undefined. All right. Now, everybody, it asks us to find the domain. Find the domain of U composite V. It says use the steps that we just did together. All right, use those steps. Now, first of all, everybody, tell me about V. What's the domain for V of X? This function right here. What's the domain for V of X? That's where I'm putting X first, right? I just found out I couldn't put a negative number in there, right? Negative 4 is undefined, so I can't put negative numbers in there. But I can put a number that's greater than or equal to 0, right? So for V of X, the domain, right, is from 0 to infinity. That's 100% correct. All right? That's my domain for V. Now, look at these numbers right up here, everybody. Look here. All these values I got are real numbers, obviously, right? 0, 1, 2, those are all real numbers. Perfect. Everything works great. Until what happens? Look at U of V of X. What happened there? Do I get positive outcomes? Do I get real numbers for all those? Not the output, right? Look right here. What do I get? Undefined. Because why? If I look back over here to this guy, I can't put 2 in there. There's no way. I can't put a 2 in there because it makes the denominator 0, which makes it undefined. So the domain of U of X, the domain of U of X here, everybody, is X cannot equal plus or minus 2, right? X cannot equal plus or minus 2, which means I go from negative infinity to negative 2, right? Union with negative 2 to positive 2, union with 2 to infinity, right? That's my domain. But for V, my domain has to be from 0 to infinity, which means everybody down here, I have to exclude this. I can't have this. I can't have this domain because we already saw we can't put negative 4, we can't put negative 2, we can't put anything that's less than 0. So my domain for my composite function must start with this domain V of X. Right? So the domain for U of V of X is equal to this domain, right? That's the main set, this domain right here. And then I have to take out anything else that won't work. And notice what it won't work up here, everybody. 2 won't work. Everybody see that? So I cannot include 2 in that domain. We saw that it makes it undefined. Right here, it's undefined. So my domain is from from 0, not including 2, union with 2 to infinity. You see how I have to pull that 2 out of there because it can't go into U. U cannot handle that value. So when you're doing the domain of these functions, everybody, consider first of all, what can I put into V of X? That's the first step. What can I put into V of X? And we saw that right here, anything greater than or equal to 0. Then I ask myself, is there anything in that domain such that that output makes my other function, my larger function, the U in this case, that makes that undefined? And if so, I have to take that value out of my domain. So it's a 2-step process. Domain for my inside function, consider that range. Does it make anything in my other function undefined as well? So 2-step process. Anybody have any questions here? All right, it says use a table to find the values of the indicated compositions. Let's rewrite this, okay, so it makes sense to us. We're going to write this as P of Q of 3. All right, that's what we're going to do. So everybody, step 1, first step, what is Q of 3? Look at the table. What is Q of 3? There's X, there's 3, there's Q of 3, which is 0, right? Q of 3 is 0. Perfect. So Q of 3 is 0. Next, what is P of 0? That's my outside function now. What's P of 0? Here's 0. There's P of 0 right there. It is 9. All right. So that tells me that P of Q of 3 is 9. Check. I'm done. All right. You guys try the next one. What would Q of P of 2 be? Q of P of 2. Q of P of 2 equals what? What's the 2-step process that can help me determine that? All right. Is it 5, everybody? What do you guys think? Is it 5? What's the first thing I want to find? I want to find what is P of 2. That's the first step. So go back over here, go to my chart, look at the value for P of 2. All right, here is X equals 2. There is P of 2, which is 1. So P of 2 is 1. So in place right here, right? In place of P of 2 right there, I'm going to put 1. P of 2 is 1. So I want to find Q of 1. What is Q of 1? Go back over here to my table. There's 1. There's Q of 1, which is 5. Q of 1 is 5. Therefore, Q of P of 2 is 5. All right, you guys see if you can figure out how to use the graph. See if you can use the graph rather than a table. See if the graph helps you out. All right, so let's write it out step by step. All right, this is W of Z of 3 equals what? All right, so first of all, what is Z of 3? That's step 1. What is Z of 3? All right, if I look at my graph, here's 1, 2, 3. So Z of 3 is right there, and that is 2. So that is the point 3, 2. So that is 100% correct. Z of 3 is 2. Next, I want to find W of 2, right? I'm going to replace the Z of 3 with 2. And that's what I'm going to put right here for my answer. So looking at my graph again, what is W of 2? Looking at my graph. Can you guys see that graph okay, or is it hard to see on your side? Can you see the graph fully? Okay. All right, so I found Z of 3 is 2. What is W of 2, everybody? Oh, Scott has it. It's 0. That's correct. It is 0. So W of Z of 3 is 0. Okay, we got one more to do. This time we want to find Z of W of 4. Z of W of 4 equals what? All right, step 1 is, what is W of 4? Looking at my graph, what is W of 4? All right, let's look at the graph. There's 4. There's my graph of parabola. Is W, is that parabola? It's right there, which is 100% correct. All right, what is Z of 1? Here's 1. Z of 1 is 3. Perfect. It's 3. Therefore, Z of W of 4 is equal to 3. How you guys feeling about this? Everybody feeling okay? Is it working out a little better? That's good. All right, we're going to do a little application question here. This will be our last question here for the night. A circle initially has a radius of 3 inches. It begins to expand in such a way that the radius gains 2 inches every 30 seconds. Fill in the table below. All right. So my circle originally has a radius of 3 inches. So I have a circle. Right? It has a radius of 3 inches. Okay. Then it says it starts to expand such that the radius gains 2 inches every 30 seconds. All right. Let's try filling in the table. When t is 0, what's the radius of this circle, everybody? 3, right? Exactly. 3. All right. At 1 minute, what's the radius of the circle? You tell me, well, it is 2 times 30. Is that right? Not 30, I'm sorry. Every 30 seconds it grows 2 inches. So in 1 minute it's grown twice, right? So 2 times 2 plus 3, which is 7, correct. All right. What will the next one be? See if you guys can fill out the table the rest of the way. All right, for the next one, at 2 minutes, it's going to be 2 times how many 30 seconds do I have in 2 minutes? I have 4, right? 2 times 4 plus 3. In 3 minutes time, what am I going to have? 2 times how many? 6 plus 3. All right, so what I want you guys to do is see if you can write a formula for that, right? That's what we're trying to do. How could I write a formula for that? This is 7, right? Could I write a formula that would help me to be able to express the radius as a function of time? All right, good. Caden says 2 times 2x, that'd be 2t, right? 2 times 2t plus 3. Like we said a moment ago, we're going to multiply 2 times how many 30 seconds there are, right? So plus 3, that's 11. So this one is 11. What's the next going to be? 3, 7, 11. What's the next one going to be? Right? 15. And the last one is going to be 19. Perfect. So it's going to be 2 times 2t plus 3, which is 4t plus 3. That is correct. So the radius as a function of time is 4t plus 3. Does that give us the right amount of time we want? Let's check and see if our formula is correct. We may need to revise it. Let's try it. All right, r of 0 is 4 times 0 plus 3 equals 3. R of 1 is equal to 4 times 1 plus 3, which is 7. R of 2, which is 4 times 2 plus 3, which is 11. Okay, R of 3 is equal to 4 times 3 plus 3, which is 15. Those all check out, okay? So our formula is correct. Now, everybody, see what you can do with the radius. I'm sorry, the area. Well, that begs the question of what's the area of a circle, right, everybody? That's the question. What's the area of a circle? Area of a circle is pi r squared, right? So the area at 0, they told us it was 3 when t was 0, okay? So this would be 9, right? What's the next one? 9 pi, rather. Just keep going, right? If the radius is 3 inches, it's 9 pi. If the radius is 7 inches, it is 49 pi. If the radius is 11 inches, it's 121 pi. Right? If the radius is 15 inches, that's 225 pi. And so forth and so on. So if I want to express the area as a function of the radius, I would say area equals pi r squared. If I want to express the radius as a function of time, right? Function of time, I would say A equals 4t plus 3 squared times pi. Perfect. Exactly right. And that concludes that, everybody. So When you're working on these guided notes, if there's something that I didn't fill in, make sure you come back through and fill it in later as you are able to, okay, as you're working on the homework. We have completed that for the night. All right, everybody. So, question for you guys to decide. It's up to you. Would you like to go for the evening, or would you like to go back and take a look at some homework questions? You may do whatever you would like to do. If you would like to stay and work on some homework questions, we have 10 minutes left in class. If you would, and you can ask me whatever questions you want to. If you'd like to go for the evening, feel free to sign out, have yourself a good evening, and we'll catch up next week. It's 100% up to you guys. If you've had enough fun for one night, go ahead and check out. Thank you guys. All right, we got 4 of us left. If you guys are staying and you want to do some homework questions, feel free to do so. I'm here to help you if you like. You can work on any assignment you like. Doesn't matter to me. This one, 14, 15, or 16, any lesson you have you want to work on, go for it. All right, Scott, very good. Have a good evening. All right, see ya. Have a good night.